Let's just picture this for a second. You're out on a massive offshore platform. You're surrounded by ocean, millions of cubic feet of flammable hydrocarbons are actively flowing right beneath your feet, and you need to flip a light switch. So what happens when a single spark meets an offshore gas leak? Well, it's a literal life or death question, right? And answering it correctly is the absolute foundation of hazardous area engineering. When we're dealing with explosive gas atmospheres on ships, FPSOs, or offshore platforms, every single piece of electrical and mechanical equipment has to be rigorously designed to prevent a total catastrophe.
Welcome to This Explainer. Today, we're unpacking the incredibly precise, high-stakes world of hazardous area classification and equipment certification. We'll be pulling directly from international standards like IEC 60079-14, DNV offshore standards, and some real-world ATEX equipment certificates. But keep in mind, just knowing the theory isn't the same as being certified to actually do the work. So we're going on a journey from the macro level, mapping out a massive offshore facility, all the way down to decoding a single equipment tag. And along the way, we'll talk about the strict installation rules and the internationally recognized personal certifications like CompEx and IECEx that prove you're actually competent to keep everyone alive.
Okay, let's dive right into this. Here is our roadmap for cracking the code of hazardous area safety. 1. The risk of explosions. 2. Defining the hazardous zones. 3. Equipment protection methods. 4. Decoding ATEX certificates. And finally, 5. Safe installation rules.
Section 1. Defining the hazardous zones, mapping the danger.
Now, engineers don't just guess where a fire might start. They follow incredibly stringent standards to divide a facility into categorized zones, all based on the actual probability of explosive gas being present. You can see the progression right here. In Zone 0, marked in red, the presence of explosive gas is continuous. We're talking about the environment literally inside cargo tanks or slop tanks. Moving to Zone 1, those orange areas like process modules and pump rooms, gas is likely to occur occasionally during normal day-to-day operations. And then in Zone 2, the yellow areas, explosive gas is only present under abnormal conditions. So think of a sudden leak near a relief valve. And finally, of course, you have your non-hazardous gray areas like the living quarters.
The absolutely crucial takeaway here is that you cannot buy or install equipment until you know the specific zone. Zone 0 demands the highest level of protection, specifically intrinsic safety, or EXIA. Move out to Zone 1, and you can start using explosion-proof, or XD, equipment. And then out in Zone 2, you get a bit more flexibility with non-sparking XN equipment. Look, if you put standard, everyday industrial-grade equipment anywhere but those non-hazardous areas, you've essentially created a ticking time bomb.
Section 2. Equipment protection methods, the alphabet soup.
Now, what's really interesting about this is how our sources from the Engineering Hazardous Area Safety Atlas simplify these confusing acronyms into really practical, memorable rules. First up, we have XD, which stands for flame-proof enclosure. The rule to remember? XD is durable, cools the flame, saves the game. The concept here actually isn't to prevent an explosion from happening inside the box. Nope. Instead, the enclosure is just incredibly strong. So if an internal explosion does occur, the hot gases are forced out through a highly specific engineered gap width. By the time that gas escapes the enclosure, it has cooled down so much that it literally cannot ignite the explosive atmosphere outside. It's a really brilliant piece of engineering.
Next is XE, standing for increased safety. The phrase to remember is, E is for extra care, no sparks in there. Unlike XD, an XE enclosure is absolutely not designed to contain an explosion. Instead, it relies on exceptionally high-quality insulation and incredibly secure connections to ensure that arcs, sparks, and hot surfaces simply never happen during normal operation.
Then we have XI, or intrinsic safety. The rule here is I is impotent, the spark is too weak to bite. We see this used a lot for sensors and control room barriers. This method intentionally restricts the electrical energy in the circuit to levels so incredibly low that even if a spark does happen, it physically lacks the thermal energy to ignite the gas mixture. It just can't do it.
Finally, there's XN, which is a non-sparking protection method. This guarantees no arcs, no sparks, and no hot surfaces, often using restricted breathing enclosures. But be super careful here. As the DNV rules explicitly state, XN is strictly reserved for those lower-risk Zone 2 environments. There is absolutely no way you can use this in Zone 1 or Zone 0.
Section 3. Decoding ATEX certificates. Cracking the code. So we know the theory, but out in the field, this has to be proven by technical paperwork. And this is where we have to talk about ATEX. When you look at an equipment tag, you'll see a string of characters that honestly looks like a secret cipher. Let's break down EXD-ICT6. EX indicates it meets the European X standard, specifically the ATEX 2014/34/8U Equipment Directive. Think of this exact directive like a vehicle's roadworthiness certificate. It is manufacturer proof that the equipment itself is built correctly for explosive atmospheres. The D tells us it uses that flame-proof protection method we just looked at. IIC refers to the gas group, in this case the highest risk group, which includes highly volatile gases like hydrogen. And finally, T6 is the temperature class, meaning the equipment's maximum surface temperature will never ever exceed 85 degrees Celsius, keeping it safely below the ignition temperature of the surrounding gas. Let's look at how this applies to a real-world document from our sources. Here are the specs for a Fisher-Rosemount digital valve controller. It holds an ATEX certificate from the LCIE notified body. Notice the rating right there, I, 2, G, and D. The Roman numeral I means it's for surface industries, not mining. The 2 means it's Category 2, making it suitable for Zone 1. G and D means it's rated for both gas and dust. Its protection method is XD, rated for gas group IIB plus hydrogen with a T5 temperature class. It's basically like reading a very specific resume for a piece of steel.
Let's check out another one. This is an MEDC brake glass unit, certified by BASIFA. What's absolutely fascinating about this one is that the certificate explicitly dictates exactly what goes inside it. It states that the unit must incorporate certified XE or XI terminals, and it literally lists the approved components, like the Wiedmuller Type AKZ4 or the Phoenix Kerr X ceramic terminals. You can't just swap in any random terminal you bought at the hardware store. Doing so instantly invalidates the entire certificate.
And that brings us to a massively important rule, highlighted in the DNV Offshore Standards. Buying an empty certified XT flameproof box is not enough. An empty box is just an empty box. Once you put equipment inside it, you alter the free volume, which directly alters the potential explosion pressure. Because of this, certified empty XT boxes must have a final certificate that specifically takes into account the exact equipment installed within it during the build.
Section 4. Safe Installation Rules, where theory meets steel.
And this brilliantly illustrates our next point. A flawless piece of equipment is totally useless if the physical installation on the steel deck violates IEC standards. Legally installing this brings up a totally separate directive, Directive 1999/92/EC, which is the Workplace Directive. This is where personal competency comes in. You need your driving license to install this gear. Whether that's the UK-rooted CompEx scheme, which is huge for electrical and instrument techs, or the internationally recognized IECEx units, you have to know the physical rules. For example, remember how XD enclosures vent hot gases? Well, the DNV rules state strictly that XD enclosures cannot be installed too close to a bulkhead or solid object. For gas group 2A, you need a minimum of 10 millimeters of spacing. For 2B, it's 30 millimeters. And for the highly volatile 2C gases, you need at least 40 millimeters. The flame absolutely needs this exact room to vent and cool safely. If you block it, the enclosure fails.
And here is a brutally practical warning straight from the Safety Atlas. Do not paint flanges. I mean, it seems like a great idea to prevent rust, right? Well, congratulations, you've just built a bomb. The gap between the metal flanges on an XD enclosure is engineered down to the fraction of a millimeter to cool an escaping flame. If you slop a thick coat of paint on those flanges, you completely ruin that engineered gap width. When an explosion happens, the paint will burn, the gap will widen, and that internal explosion will punch right through to the outside atmosphere. Just don't do it.
Now, there are highly specific rules for wiring too. When you're dealing with XI intrinsically safe circuits, DNV stipulates that the braid, armor, or collective screen provided in the cables must be connected to the local earth at both ends. It might also be earthed at intermediate junction boxes. This is absolutely critical because it ensures that any errant currents or static buildups are safely neutralized and never, ever allowed to generate an incentive spark.
The same strict rules apply to rotating equipment, like motor installations. Say you have a certified XE increased safety motor, and you want to control its speed with a power frequency converter. The DNV standard explicitly states you cannot just slap a frequency converter onto an XE motor in a Zone 1 area. Because the converter alters the thermal characteristics of the motor, the converter and the motor must be explicitly certified together. The certificate literally has to state that they are an allowed combination.
So what does this all mean? We've gone from the macro classification of offshore zones right down to the exact millimeter of spacing required for a steel enclosure. The engineering here is brilliant, but it relies entirely on execution. The provocative question you have to ask yourself every single day on a platform is this. Sure, your equipment has the ATEX equipment certificate, but do you have the personal CompEx or IECEx competency to install it? And does your physical installation actually respect the zone? I really hope this explainer has given you the tools to ensure your answer is always a confident yes.